Hiya Jacob, this is your feedback video for the Circular Motion 2 homework. Let's have a look at question 1. So question 1, they want you to label the forces acting on the car. Right, okay. A couple of things. So you've labeled the reaction force, which is good. It should be the same size as the weight, okay, because vertically the car's in equilibrium, okay. You've correctly labeled the reaction. Oh, I'm sorry, you have done. I didn't see that the arrow's this long. Sorry. Yeah, that's good. And here you've labeled it so it's perpendicular to the surface, which is good. However, there's a couple of things here. Centripetal force is not a real force. The centripetal force is the resultant force. It's the kind of it's the vector sum of all the real forces acting on the object. So we don't label it on the diagram, okay, because it's not a real force. So this shouldn't be here, this shouldn't be here. Okay, now let's talk about friction. You've got your friction arrow acting the wrong way. Okay, you got to try and think friction is going to oppose the motion of the car. The center of the circle's over here, so the car is, think of it like this, the car's trying to slide that way. So the friction acts the opposite way. The frictional force actually acts like along like here. That's friction. Okay. In this diagram, it's the opposite way. It's that way. That's the friction. The car's trying to slide up the slope. If there was no, think about what would happen if there was no friction. What would happen if it was a really icy road with zero friction, and the car's trying to go round a roundabout where the center of the roundabout's over here? The car's going to skid off that way. Friction will oppose that kind of attempted slide that way. So the friction acts up here. In this diagram, the car would slide up the slope, right? Friction will oppose it. So, okay, let's talk about part 2. So, what are the possible origins of the centripetal force in figure 2? In other words, it's asking what forces are providing the centripetal force. This is the horizontal component of the reaction force. Excellent work. Excellent. Yeah, contributes to the centripetal force. Because friction acts parallel to the slope, it does not act horizontally. No, this bit's not right. You got the reaction force bit correct. But the friction force also has a horizontal component. I think the reason this is wrong is because you thought friction acts this way, but think about it, it acts this way. This force has a horizontal component. You have to add that component to the horizontal component of the reaction force, okay? And that will give you the overall resultant force, the overall centripetal force. This is good. Okay, I'm going to add up your marks at the end. Okay, I'm going to speed this up a bit because I spent ages on question 1. Yeah, looks good so far. Yeah, that's good. Well done. Yeah, you get full marks for that question. Nice work. Question 3, the package going over the humpback bridge. Interesting. We're labeling the forces on the parcel, not just the parcel, not the van, so there should be no friction. I mean, the parcel isn't sliding along the floor of the van, is it? So there's no friction force, there's no driving force, so this is not correct. The only forces acting on the parcel are its own weight and the reaction force of the floor of the van on the parcel. You need to put the word force in there as well, okay? Right, write an equation. Yeah, this is fine. But we want to make R the subject of the equation, so I'd prefer it if you wrote it like this. Actually, wait a minute, is this correct? Let me think about this. Yeah, hang on. Yeah, sorry Jacob, yeah, that is correct, yeah, but maybe write it as R equals mg minus mv squared over R, and then, okay, well done, that's correct. Right, let's have a look at this. If it went higher, excuse me, if it went faster, the magnitude of R would increase. Unfortunately not, that's not correct. Interestingly, although this isn't right, this bit you've put here is correct. Okay, let me just talk about this first. You've said it would increase. It actually decreases. Let me just show you why. Look at the way I've written the equation, okay? R equals the weight of the package minus mv squared over r. The weight of the package, mg, that's a fixed number. That's not going to change, right? Think of it like a constant. But if v is faster, this term here will increase. So your value of r will go down. Because when v is larger, you're doing mg, which is a fixed number, minus a bigger number now. So r will decrease. Okay, so that's how you want to explain this bit here. Now you've correctly said that if the speed exceeds about 15 meters per second, the reaction force will become negative. The parcel will accelerate toward the center of curvature and will break through the floor of the van. No. Right. Okay. At this speed, the reaction force is 0. The significance of that is it's quite the opposite of this. When the reaction force is 0, that means that the parcel has lost contact with the floor of the van. It's actually lifted off the floor. Okay, so you need to do a bit of work on this question here. Okay, come and speak to me if you want me to clarify anything. Okay, let's just look at this last one. Okay, good. This here is not right. Okay, there's a couple of ways you can do this, okay? You can either, what you can do is you can use this equation, you can let F, which is the tension, be 60 and work out V. Once you've got the velocity, how could you use that number to work out the number of revs per second? Okay, it involves the circumference of the circle. Okay, there's a hint for you. The other way you can do it is to use F equals mr omega squared. You can find omega, and then from that you can find the frequency. To redo this question. Right, this looks good. I like this diagram. Right, let's have a look. So, okay, that's pretty good, yeah. A force must act on the object. Right, this is good. Direction's changing, so the velocity's changing. Acceleration is produced when a force acts on a mass. Yeah, use the term resultant force, okay, instead of just a force. Put resultant in there. This is good. I like all of this. Well done. Yeah, you've said that this resultant force acts toward the center of the circle. Good. Newton's third law. Right, so you've stated generally what Newton's third law is. This suggests that the ball creates a tension in the string which exerts a force on the central point that swings the object around. This force is equal to the force that the point acts on the object. Yeah, well done. Very few people got that. This is outstanding, Jacob. This is outstanding. Absolutely spot on. I think this is, I mean, you're not going to get a question harder than this on circular motion. You've done really well there. Okay, so good work. A couple of corrections to make, but yeah, overall, I'm really impressed with this. Well done.